Okay, welcome to section 2, which is simplifying square roots. And hopefully the first thing you see is this table that I have, because we're going to use this table again because this table is so important for us. Now, this section, we're going to actually find what we call exact values of square roots. All right, so for example, in the previous section, we know that the square root of 20 is somewhere in between 4 and 5. And when we used our calculator, we got 4.47 as an approximation. All right, that's just an approximation. What we're going to do today is I'm going to show you how to get the exact value. Okay? Now, the key to this entire section, the key to this entire square root thing is we need to think perfect squares. Now, all this entire second row, those are all perfect squares. So 1 to the second, we know is the same thing as the square root of 1. The square root of 4 is 2 because 2 to the second equals 4. The square root of 9 is 3 because 3 to the second power is 9, and so forth. So if I wanted to find the exact value for the square root of 20, what I'm going to do here is I'm going to ask myself, are there two numbers that I can multiply that'll give me 20? And here's the key, or here's the catch. One of the numbers is a perfect square. All right? And what I mean is one of those numbers has to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth. Well, it just so happens that 4 times 5 equals 20. Now, we're going to learn, before we can do anything further, I'm going to show you the product property of square roots. Okay, so we no longer need this stuff. All we need is this. Okay, so the product property of square roots says that if I have the square root of two numbers, it can be a bunch of numbers, okay? It could be as many numbers as I want underneath. But these two numbers, A and B, are non-negative. So they got to be positive numbers. Then the square root of A times B is the same as the square root of A times the square root of B. In other words, as long as I am multiplying whatever I have underneath that square root, I'm allowed to separate them. I can break them up into their own little square root problems. So if you think about it, the square root of 20, I can rewrite that as the square root of 4 times 5, which means I can break this up into the square root of 4 times the square root of 5. And here's the best part. We already know that the square root of 4 is 2. So the square root of 20 in its exact answer, or its exact form, is 2 times the square root of 5. Now, let me show you that what I'm saying is truth. So we're going to go ahead and we're going to type both of these into my calculator. So the first thing, we're going to do the square root of 20. So the square root of 20 is already there. But now let's type in what we found the exact answer, which is in the lower right-hand corner. 2 square root of 5. And watch when I hit enter. It is the same exact value. And that's because 2 times the square root of 5 is the simplified version of the square root of 20. So, as I said earlier, the key to this, the key is finding numbers that are perfect squares, and then you want to apply this product property. Why did I write product twice? The product property of square roots. So, I know it's a lot easier said than done. So let's go ahead and let's do just a bunch of examples right now. So we're going to do the square root of 50. Square root of 50 is definitely not on our chart. But what I do know is that 50 is really 25 times 2. Now, the reason why I chose 25 times 2, because think about it. You could have did 5 times 10. 5 times 10 is still 50. However, I'm looking for perfect squares. And 25 is one of those perfect squares. So, I can separate them. And now reduce. The square root of 25 is 5 times the square root of 2. Okay? Let's go ahead. Let's do the square root of 45. So, square root of 45 is 9 times 5. Which means I can break them apart. I know the square root of 9 is 3. Square root of 5 doesn't reduce at all, so it just stays as 3 square root of 25. Okay? Now, sometimes it's easy. These numbers are very simple. What about something like the square root of 288? Well, I know you've heard me say this before in this class, and you're going to hear me say it a lot, even if you take me for Math 108. I love this technique called prime factorization. If you go back and look at our Chapter 8 videos, I do this a lot. All right? So I'm interested in two numbers that multiply to give me 288. So I think the easiest two are going to be 2 and 144. Now, I can stop right here. I know 2 is a prime number, and I know 144 is one of those beautiful perfect square numbers. So I can separate them. I know the square root of 144 is 12. Square root of 2 doesn't reduce, so we leave it as a square root of 2. Okay? So I hope this is making some sense. I really do. Okay? But what about this number? How about the square root of 80? All right? Well, if you can't think of a perfect square, all you got to do is prime factorize. Watch how beautiful this is. I know I can break down 80 into 2 times 40. 2 is prime. I know I can break down 40 into 4. 4 times 10. Now, there's that perfect square I'm looking for. Okay? But also, 10 can break down into 2 times 5. And they're both prime. Now watch what I do here. I'm going to write the 4 out front because I know that's a perfect square. Then I'm going to multiply it by 2 times 2 times 5. But if you look, we know what 2 times 2 is. 2 times 2 is 4. So notice I have the square root of 4 times 5. And we know if we break these up, we can get our exact answer. I'll just come straight down. Square root of 4 is 2 times. Square root of 4 is 2 times the square root of 5. And 2 times 2 is 4. Square root of 5. So, I guess if I just want to just kind of summarize this. So, the square root of 80 equals 4 times the square root of 5. Now, if you're asking yourself, well, what about variables? Well, let me show you. How about the square root of 3, or x to the third? Now, we are going to do this the same exact way that we did all the other variable problems from previously. Watch. 2 goes into 3 once with a remainder of 1. This number 1 is going to be the exponent outside the radical symbol. Your remainder is the exponent inside the radical. Notice the difference. So the square root of x to the third is x to the first times the square root of x. All right? Now, let me do another one like this. I'm going to write it right here so you can actually see like the major difference, okay? So we're do the same thing again. We're going to take the square root, but this time let's do x to the, we'll do the 13th power, okay? So I know I'm going to divide by the index. So 2 goes into 13 twice. Oh, sorry, geez. 2 goes into 13 6 times with a remainder of 1. Now remember, the 6 is going to be the exponent outside of the radical. So it's going to be x to the 6th. The remainder is going to be the exponent on the inside of the radical. So it's x to the 1st. Okay? So the square root of x to the 13th is equal to x to the 6th times the square root of x. And now we can bridge both ideas together. We can use numbers and letters together. All right, so the square root of x, the square root of 16 times x to the 7th, well, the square root of 16 we know is 4. Now I got to worry about that x to the 7th. Remember, the index is a 2. 2 goes into 7 3 times with a remainder of 1. So this is going to be, remember, the 3 is the exponent outside, x to the third, and then the 1 is the exponent on the inside, x to the first. So it's just 4x to the third times the square root of x, and technically you don't even have to put that 1 there. You can just leave it as 4x to the third times the square root of x. Now let's try another one. How about the square root of 32 y to the 9th? Okay, well, with this one, we're going to have to do a little bit of work. We know 32 is really the square root of 16 times 2. Okay? Now I'm also going to tack on the y to the 9th. Now the reason why I did that is so I can separate the square root of 16 times the square root of 2y to the 9th. I know the square root of 16 is 4. The only thing I really got to worry about here is y to the 9th. So 2 goes into 9 4 times with a remainder of 1. So this is going to be 4 y to the 4th times the square root of 2y to the 1st. Notice the 2 stays on the inside because I can't further reduce that. All I had to do was reduce the y to the 9th. Okay? Now I can even get even more in depth with this. Let's do the square root of 63, x to the third, y to the 4th, z to the 9th. All right? If you take this one step at a time, it's easy. First things first, let's worry about the number. 63 is really 9 times 7. Oops. And I'm just going to rewrite my variables. Now I know the square root of 9 is 3. So I'm going to put a 3 here. And if you wanted to, you can leave yourself a little bit of space and put a 7 on the inside. So now the square root of 63 is done. It's 3 square root of 7. The question becomes, I got to worry about these variables. So I'm going to put an x, a y, and a z. And we'll do each of them. 2 goes into 3 once with a remainder of 1. So I got 1x on the outside, 1x on the inside. Now let's do the letter. Now we're going to do the letter y. 2 goes into 4 twice with a remainder of 0. So I have 2 y's on the outside and no y's on the inside. I'm going to move this over. Okay, I just wanted to make a little bit more space. Now for the z. 2 goes into 9 4 times with a remainder of 1. So I have 4 z's on the outside and 1 z on the inside. So the square root of 63, x to the third, y to the fourth, z to the ninth, reduces down into 3x, y to the second, z to the fourth, times the square root of 7 times x times z. Nobody said these were pretty answers. They are absolutely atrocious looking. But they are exact and they are correct. Okay? So maybe you're sitting there and then you're asking yourself, okay, well, why are we doing all this? Okay, why are we doing all this? And the answer is because eventually we want to be able to add and subtract square roots. Okay? In other words, our goal at the end of the day is going to be something like this. We want to be able to add the square root of 2 plus the square root of 8. Now, right now, you can't add these together because they're not the same radicands. All right? We want them to both be the square root of 2 or both be the square root of 8. That's not the case. However, we know the square root of 8 is really 4 times 2. And the square root of 4 is 2. And then the square root of 2 stays the same. So we can rewrite the problem as the square root of 2 plus 2 square roots of 2. Now the radicands are the same. So really what you're concerned with is what is 1 plus 2. And 1 plus 2 is 3. So the square root of 2 plus the square root of 8 is the square root of 2 plus 2 square roots of 2, which turns out to be 3 square roots of 2. Okay? So that's what we're gearing up to. But before we can do that, let's just go ahead and let's look at a couple more examples. And then we can call this a day here. What if we had something like this? What about the square root of 25 over 16? Well, we know that the opposite operation of multiplication is division, and our rule would still apply then. In other words, we can separate this as the square root of 25 divided by the square root of 16. Square root of 25 is 5. Square root of 16 is 4. So it's just going to be 5 over 4. We could extend this even further. We could do something like this. Let's say the square root of 45 over the square root of 48. First thing I would do is separate. And then from here, I would treat them like two little mini problems. In other words, square root of 45 is the square root of 9 times 5, which turns out to be the square root of 3 times 5. Now the square root of 48. I had to think about this one for a second. 16 times 3. Actually, let me write it the same way I have it above. So the square root of 48 reduces down into the square root of 16 times 3, which is really 4 square roots of 3. So if you look at what I have at the very end, right here, I'm blocking it in. The square root of 45 over 48 is equal to 3 square root of 5 over 4 square root of 3, which is your final answer. So even though they're fractions, nothing changes. Your technique is still the same. You are looking for perfect squares so that you can separate them and reduce them very quickly. Okay? And that's going to be it for this video. I will see you in the next one when we talk about adding and subtracting square roots.